All right, guys, we are going to take up where we left off, and we are going to talk about how we actually do the calculations of boiling point elevation and freezing point depression. So let's get back to our notes where we left off, and we will start using these formulas. Okay, so we talked about freezing point depression, and we talked about boiling point elevation. So if you remember, our change in temperature is equal to our boiling point constant times the molality, and that's for our boiling point, and our freezing point is pretty much the same. We have our freezing point constant times our molality. Okay, so let's talk about this. We want to calculate the boiling point and the freezing point if I have 300.0 grams of C2H6O2, and that is ethanol, and dissolved in 800 grams of water. So molality, if you remember, molality, little m, is number of moles of solute divided by kilograms of solvent. So hopefully you are realizing that this is our solute and this is our solvent, right? So the very first thing we've got to do is calculate our molality. So we've got 300 grams of C2H6O2, and I need to get that into moles. And I have 800 grams of water, and I need to get that into kilograms. So let's see. The first thing we've got to do is I've got to figure out how many grams of C2H6O2 are in 1 mole of C2H6O2. So I've got to find my molar mass. So let's see. I've got 2 carbons, and I've got 6 hydrogens, and I've got 32 grams of oxygen in there. So my molar mass comes out to be 62.08 grams. So I've got now moles on top, which is what I want. Now I need to get kilograms. So grams to kilograms, I have 1,000 grams in 1 kilogram. Okay, so grams are canceled. My grams of C2H6 are canceled. I have moles per kilogram. So let's do some calculations now. So 300 divided by 800 divided by 62 times 1,000. So that gives me, let's see, I've got 4 sig figs, right? So 6.048 is my molality. Okay. So the next thing I've got to do is I've got to figure out what my boiling point constant of water is, because my solvent is water. So let's look at that. We're going to have scroll here. My boiling point constant for water is 0.512 degrees Celsius per mole. Okay. So we're going to use our boiling point constant, 0.512 degrees Celsius per mole, and our molality is 6.048 mole. So my molalities cancel out, and I just have temperature, which is my change in temperature. So I'm going to do the multiplication here with 3 sig figs, right? I've only got 3 sig figs there. This will give me a change in temperature of 3.09 degrees Celsius. So I know my boiling point then is going to be added to the normal boiling point of water. And the normal boiling point of water, so this is my change. Okay, that's my change. So if I want to know my actual boiling point, I'm going to add it to the normal boiling point of water, which is 100. So 3.09 plus 100, I would expect this to boil at 103.09 degrees Celsius. Okay, that would be my new boiling point with that solution. Okay, we can do the same thing with our freezing point. So we need to look up our freezing point constant of water. So if we look at our freezing point constant of water, it's 1.86 degrees Celsius per molal. Okay, so freezing point constant of water, 1.86 degrees Celsius per molal. And our molality is 6.048 molal. So let's do that math. So 1.86 times 6.048, we've got 3 sig figs. So with 3 sig figs, I would expect a change of 11.2 degrees Celsius. Now my normal freezing point of water is 0, and this is freezing point depression, which means I've got to subtract it from 0. So this is my change. My new freezing point would be negative 11.2 degrees Celsius. Okay, so let's do a few more examples here. Example 23. If I've got 23 grams of an unknown compound and I've dissolved it in 1,000 grams of water, the freezing point is now observed to be negative 0.93. What is the molecular weight of the compound? Now you're probably going, oh my gosh, there's no way. Okay, you can do this. If I know the freezing point depression, I can get the molality of that solution. And if I know how many grams were put in that solution, I can figure out the molecular weight of that compound. And maybe matching it with other compounds, like a list according to molecular masses, I might be able to figure out what that compound is. Okay, so to find molecular weight, we need to know 2 things. Okay, we need to know grams, and we were given grams. How many were given in that? And we need to know moles. We need to know the number of moles. I can figure out the number of moles because I need to figure out molality, and I have the amount of kilograms of solvent that was used, so I can figure out moles. So here we go. We are going to isolate our molality here. So notice I've taken this formula and I've solved for molality. So our change in our freezing point, what's the normal freezing point of water? Isn't the normal freezing point 0 degrees Celsius? So if we're at negative 0.93, isn't the change 0.93? Right? Could I say that change is 0.93? So I'm going to say my molality is equal to 0.93 degrees Celsius. And I want to divide by my freezing point constant. So isn't my freezing point constant? Didn't we find it in the last question? Isn't my freezing point constant 1.86 degrees Celsius per molal for water? Okay, so that cancels out my degrees Celsius, and that gives me my molal. So I'm going to take 0.93 and I'm going to divide it by 1.86. And I get 0.5. So I have a 0.5 molal solution. And if you remember 0.5 molal solution, let's see, I have 2 sig figs, is moles per kilogram. Wasn't I given that I have 1,000 grams of solute? So I had 1,000 grams of solute. And isn't there 1,000 grams in a kilogram? So my grams cancel out. I have 0.5 moles, right? So I really comes down to it. I have 0.50 moles of the solute. So if I have the number of moles that I actually used, and I have the grams that solute was actually, so isn't the molecular mass, isn't molar or molecular mass number of grams per mole? Isn't that what we do? Okay, so I have grams. We put 23 grams into that solution. So I have 23 grams, and we determined that I put 0.50 moles in there. So 23 divided by 0.5 gives me a molar mass of 46 grams. I only have 2 sig figs here, so 46 grams per mole. So I know that the molar mass of that compound is 46 grams per mole. Do I necessarily know what it is? No. But I could find out things that are near 46 grams per mole and probably make a pretty educated guess. All right. So, number 24. An electrolyte, sodium chloride, is often used to prevent icy roads and to freeze ice cream. What are the boiling point and the freezing points of a 0.029 molar aqueous solution of sodium chloride? Now, remember, this is an ionic compound, and we have to determine on ionic compounds whether they are soluble or not. Excuse me. So, sodium chloride actually breaks into ions. So instead of 0.29 molar, don't I get 2 particles for the price of 1? I do. So now when we do this with ionic compounds, we have to add another thing for our formula. So let me show you what we do for ionic compounds. So the change in temperature for the boiling point is still equal to that boiling point constant multiplied by the molality, but we add in this little I, and I is equal to the number of ions. So for sodium chloride, we would get 2 ions here. Okay, so the freezing point change would also be the freezing point constant multiplied by the molality multiplied by I. Okay, so here we go. Our boiling point constant, if you remember, of water was 0.512 degrees Celsius per molal. And we have a 0.029 molal solution, and we have 2 ions. Okay, so when we multiply that all out, we get 0.029 degrees Celsius, right? Ish. So we only have, let's see, we have 3 sig figs. So let me check that sig figs there. Actually, we have 2 sig figs with that molality. So that would actually be a 6. So let's round it up. 30 degrees Celsius. So the boiling point is just going to go up about 0.3 degrees Celsius. So we would expect our new boiling point to be 100.03 degrees Celsius. So not a big change. Let's see how much it changes our freezing point. Now, if you remember, our freezing point constant was 1.86 degrees Celsius per mol. We have 0.029 mol, and we have 2 ions. Okay, so when we do that, we would expect, let's see, with sig figs, that gives us, let's see, 0.11 degrees Celsius. Now, this is our freezing point, so we've got to subtract it from the normal freezing point of 0. So our freezing point that we would expect would be 0.11 negative degrees Celsius. So once again, not a huge change in the freezing point or the boiling point because that molality is pretty small. Okay, so that's how you use boiling point elevation and freezing point depression calculations. All right, last but not least, osmotic pressure. You probably talked about osmosis a bit in biology, but to actually have molecules travel across a membrane, it actually creates a pressure gradient. Now, if you remember, osmotic pressure is based on something traveling from an area of high concentration to low concentration. So let's define pressure really quickly. So here on this cross section, I have it magnified here. We've got a semi-permeable membrane where we have a membrane that only allows the smaller particles to come in. And notice I have a solution here, but only the water molecules can come in because they're pretty small. So because this is pure water on this side, they're going to come in here to try and equal out that concentration. So it's going to create some pressure, some upward pressure on this. Now, if I took a piston and I pressed down on that piston with just enough force to keep this flow from happening, that would be the osmotic pressure. So it's the pressure required to stop the flow of water, usually is the solvent, from an area of high pressure or high concentration to an area of low concentration. And these square brackets, and I'm horrible at writing these square brackets, but square brackets mean concentration, specifically in moles per liter. Okay, so square brackets is another shorthand for molarity or moles per liter of solution. Okay, so our formula here is the osmotic pressure is given to us by pi times the molarity times the gas law constant R and times temperature. Now the gas law constant R is kind of, we haven't done gas laws. So this is kind of a riff on the ideal gas law. The ideal gas law is pressure PV, so pressure times volume equals N is number of moles multiplied by the gas law constant multiplied by temperature. So if I isolate pressure, pressure is going to be equal to N over V times the gas law constant and T. N is number of moles and V is volume. Isn't volume done in liters? So isn't molar concentration moles per liter? So we just substitute N over V with molarity. Okay, so it's just a reformulation of the ideal gas law. Now, the other thing that we have to figure out is this temperature in the ideal gas law is done in Kelvin. And if you remember, the temperature in Kelvin is the temperature in Celsius plus 273. Okay, so it's based off of absolute zero. Okay, and the other thing, our R, that gas law constant is 0.0821 liters atmospheres divided by mole Kelvin. So 0.0821 liters atmospheres mole Kelvin is the R, is the gas law constant. Okay? So a lot of new things I'm throwing at you because we haven't done gas laws, and this is all based on gas laws. Okay, so we are taking the pressure that we would have to put on this piston up here to stop that flow of water across that semi-permeable membrane from an area of high concentration to an area of low concentration. Okay, so let's take a look at this problem. Now, because we are dealing with stuff that is biologically induced, usually that's what we're dealing with osmosis. We are dealing with really, really large molecules. So don't be surprised when we get a ton of mass for our molar mass here. Okay. All right. If the computer will stop here. So I've got 26 grams of a solute. So I have my mass, and it's dissolved in enough water to make 0.75 liters of solution at 25 degrees Celsius. So we've got a couple of things that we've got to do. First, we've got to get our temperature into Kelvin. So 25 degrees Celsius plus 273 gives us a temperature of 298 Kelvin. So that's going to be our temperature. Okay, that's one of the first things that we've got to do. All right, and then we've got our pressure given to us in millimeters of mercury. And notice our gas law is in atmospheres. So we're going to have to convert our pressure from millimeters of mercury to atmospheres as well. So throwing all kinds of things at you. So the first thing we need to do to figure out molar mass, we need grams and we need number of moles. Okay, so we've got our grams already. So we need to figure out number of moles. So let's figure out if we can take this, where we have our osmotic pressure is equal to molarity multiplied by the gas law constant times T. Let's isolate molarity. So if I isolate molarity, I get the pressure divided by the gas law constant divided by the temperature is the molarity. Do you guys agree with that? Okay, so I'm going to take the pressure, and the pressure is given to us as 119 millimeters of mercury. Okay, we've got to change that to atmospheres. So I have 760 millimeters of mercury in 1 atmosphere. So my millimeters of mercury are gone. So I've got it changed into atmospheres. Now I am going to divide by my R. So R is 0.0821 liters multiplied by atmospheres, mole multiplied by Kelvin. So notice my atmospheres cancel out, right? Then I also have to divide by temperature. So we said our temperature was 298 Kelvin. So my Kelvin are gone. So I'm now got molarity, right? Moles per liter. Now, the thing is, we had how many liters of solution? we had 0.750 liters of solution. So there goes my liters. So this will just give me moles. Okay, so let's do that math. So 119 divided by 760 divided by 0.0821 divided by 298 times 0.750. That gives me, let's see, 4.7999 times 10 to the negative 3 moles. You guys get about that? Okay, so molar mass is grams per mole. So we have 96 grams. Oh my. We have 96 grams divided by this number of moles. So 4.799 times 10 to the negative 3. So I'm going to invert that and multiply that by 96. I really have, let's see, 3 sig figs. So this gives me 20,000. So 2.00 times 10 to the 4th grams per mole. That is a big protein there. And that's not unusual for a mass of a protein at all. Proteins are huge molecular masses. So, all right. So we have talked about vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. These are all colligative properties that are all based on number of particles, but not particle type. All right. We'll see you later. Have a great day. Bye.